This is the 12-1 lesson on theoretical and experimental probability. So our objectives today are to find the theoretical probability of an event and to find the experimental probability of an event and to be able to differentiate between the two. These are some of our vocab terms that we're going to go over today. So probability is the measure of how likely an event is to occur. Each possible result of a probability experiment or situation is what we call an outcome. The sample space is the set of all possible outcomes, and an event is an outcome or set of outcomes. So, for example, when we roll a numbered cube, our sample space is 1, 2, 3, 4, 5, and 6. When we spin this spinner that's in this diagram, our outcomes are, or our sample space, are red, yellow, blue, and green. So probabilities are written as fractions or decimals from 0 to 1 or as percents from 0 to 100%. So if we're down here at 0, then obviously 0% or 0 is impossible. The further we move across this line, the more certain something is. So again, if we get it halfway here, then that's 0.5, 1/2, or 50%. When we get all the way over here to the right, that's 1. And that would be 100%. And that would mean we are absolutely certain that something is going to occur. So when we talk about equally likely outcomes, they are outcomes that have the same chance of occurring. So when we toss a fair coin, heads and tails are equally likely outcomes. Favorable outcomes are outcomes in a specified event. So if I say I'm going to toss a coin and I call heads, heads would then be my favorable outcome. For equally likely outcomes, the theoretical probability of event is the ratio of the number of favorable outcomes to the total number of outcomes. So this means, like, let's say if I tossed a coin 10 times, I would expect to get heads 5 of those times because our probability is 50% or 1/2. That's theoretical probability, whereas what we're going to deal with in a little bit is experimental probability. So if I actually toss the coin 10 times, I might not get heads 5 of those times. I might get it 3 times. I might get it 7 times. So there's a difference between theoretical probability, that's what we expect to happen, and experimental probability, that's what actually happened. So here, each letter of the word probable is written on a separate card. The cards are placed face down on it and mixed up. What is the probability that a randomly selected card has a consonant? First of all, we have to count the number of cards. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 letters. And how many of those letters are then consonants? Well, our vowels are O, A, and E, so our consonants are P, R, B, B, and L. So that's 1, 2, 3, 4, 5. So our probability is 5 favorable outcomes, those are our consonants, over our 8 possible. When we divide 5 by 8, we get 62.5, or actually we get 0.625. And when we can multiply this by 100, or we can just move the decimal 2 places to the right. Here now, it says finding the theoretical probability. So we have 2 number cubes, and they're rolled. What is the probability that the difference between the 2 numbers is 4? So here, I want you to notice that we have all 1s on the right here, all 2s, all 3s, all 4s, all 5s, all 6s. And then the other cube changes numbers here. So we have a total of 36 outcomes here. So we have 6 columns and 6 rows. 6 columns and 6 rows. 6 times 6 is 36. And anytime we roll 2 cubes or dice, we're going to have 36 maximum outcomes. So then it says here, what is the probability that the difference between the 2 numbers is 4? So let's look and see when we get the difference of 4. So 5 and 1 gives us a difference of 4. 6 and 2 gives us a difference of 4. I don't see anything in column 3 that gives us a difference of 4. Column 5, I don't see anything here either that gives us a difference of 4. And remember that difference means subtraction. In column 6, we have 1 and 5 again, and in column 7, column 5 and column 6, we have 2 and 6. So that's 4, and so that's going to be 4 over 36 possible outcomes. 4 over 36 can be reduced to be 1/9. So that is, and there's our combinations again, 1 and 5, 2 and 6, 5 and 1, and 6 and 2. All right, so on the next one, and that if we find the actual percentage of that, we divide 1 by 9, and that gives us 11.1. Okay, so a red number cube and a blue number cube again are rolled. Our possible outcomes are 36 again. So if all numbers are equally likely, what is the probability of the event of the sum of 6? Now this time we're going to add them together to get a total of 6. So we got our 5 and 1 here, our 4 and 2, our 3 and 3, our 2 and 4, and our 1 and 5. So that's the only possibles that we could get. So that's going to be 5 over 36. And again, if we divide the 5 by the 36, that's going to be 0.139. We either multiply that by 100 or move the decimal 2 places to the right. Now to check it out, go ahead and do these and then come back to me when you're done. So this one says a red number cube and a blue number cube are rolled again. If all numbers are equally likely, what is the probability of the event that the red cube is greater than the blue cube? So let's see, where do we see that? So I see that here, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 3, 2, 4, 2, 5, 2, 6, 2, 4, 3, 5, 3, 6, 3, 6, 4, 5, 4, 6, 5. So let's count how many that is. We got 5 in the first column, plus 4 in the second column. That's 9, 10, 11, 12, 13, 14, 15. So that's a total of 15. And those are all our number combinations there. So we're going to divide the 15 by the 36. That can be reduced by 3. So that's 5 over 12. And remember, anytime we write the answers to these, we want to make sure that we reduce our fractions. And then if we divide 5 by 12, we get 0.416. Move that decimal place 2 places to the right, and we get 41.6%. Our next, check it out, says if all numbers are likely, what is the probability of the sum being 10? So here again, we're looking for any sums. I don't see anything in the first column. I don't see anything in the second column. I don't see anything in the third column. In the fourth column, I see 6 and 4. In the fifth column, I see 5 and 5, and I see 4 and 6 here. So those are 3 outcomes out of 36. And so that's going to be 1/12. And then again, if we divide 1 by 12, we get 0.083. Move that decimal 2 places to the right, and we get 8.3%. Okay, now we're going to talk about complements. Now, complements are when something does not happen. So the probability of something not happening versus something happening. So the complement can also be denoted with a prime symbol. So we say the complement of P is P prime. So when we say, I don't want E, then we'll say P accent E. So here it says there are 25 students in the study hall. The table shows the number of students who are studying a foreign language. What is the probability that a randomly selected student's not studying a foreign language? Well, let's count how many we have. So we have 6, 12, and 3. So that's going to be, what is that? 18, 19, 20, 21. So our total number of students that are taking a foreign language are 21. So we're going to use that number. So how many are not taking Spanish? So here again, we're going to do 1 minus the number that are. So that's 1 minus 21 over 25. Now, I like to change this 1 into 25 over 25 because then it's easier for me to subtract the 21 over 25 from it. And we know that anything over itself is 1. So that's going to give me 4 over 25. So when we do this, our ultimate result is going to be 16% because 4 over 25 is 16%. All right, now let's look at this next one. 2 integers from 1 to 10 are randomly selected. The same number may be chosen twice. What is the probability that both numbers are less than 9? Okay, so how many numbers are greater than 9? We're going to ask ourselves that question. So that means there are 2 greater than 9, right? Which means, so we're going to do our 1 again minus the the probability that something is greater than 9. So that's going to be 1 minus 2 over 10. So that would again be 10 over 10 minus 2 over 10. That equals 8 over 10. Right? So we get 8 over 10. That can be reduced to 4/5, right? So then we're going to multiply that 8 over 10 times 8 over 10 because it says that we are going to choose two integers, and we can choose the same number twice. So when we do two things, we're going to multiply. We're going to do this a bit more tomorrow in the lesson, but we will multiply 8 times 8 and 10 times 10. That's 64 over 100. That's 16 divided by 25. It can be reduced to that, or 64%. All right, so now you can estimate the probability of an event by using a data or by an experiment. For example, if a doctor states an operation has an 80% probability of success, 80% is an estimate of the probability based on similar case histories. Each repetition of an experiment is a trial. So in other words, I could say that I'm expecting 8 out of 10 to be successful. However, when I actually do the surgery, that's going to be the experiment, and that's going to determine whether that is true or false. The sample space of an experiment is all set of possible outcomes. So the experimental probability of an event is the ratio of the number of times the event occurs, the frequency to the number of trials. So this is how many times I tried the event down here, and this is how many times I got what I wanted. That's what the experimental probability is. So experimental probability in large numbers is often used to come up with theoretical probability and make predictions. So here we go. So it's saying here to find the experimental probability, the table shows the results of a spinner experiment. Now, if I had 4 numbers, I had a spinner split up into 4 evenly spaced numbers, then my percentage of finding the actual theoretical probability of a 4 would be 25%, right? However, this is an experiment, so we're going to see if that actually occurs here. So the first thing we need to do is add up these numbers, 6, 11, 19, and 14, and when I do that, I get 25. I get 50. So then, how many times did we get a 4? We got it 14 out of 50 times. So we're going to do the 14 over the 50. That reduces to be 7 over 25, and it actually is 28%. Again, that would have been 0.28, and then we move that decimal 2 places to the right. So that was actually a little bit higher than we anticipated. So it was 28%. So remember that an experiment is oftentimes not the same as what we thought would happen. But the more times we do an experiment, the more likely it is to equal whatever the theoretical probability is. So here again, the table shows a spinner. This time it says what would be the probability of spinning a number greater than 2. So again, our total number was 50. What numbers do we have that are greater than 2? The 3 and the 4. So we're going to add the 19 and the 14. And then we're going to put that over the 50. So that's 33 over 50, and 2 times 50 is 100. 2 times 33 is 66, so that would have been 66%. So go ahead and do these 2 check-it-outs and then come back to me. The table shows the results of choosing one card from a deck of cards, recording the suit, and then replacing the card. So again, the first thing we have to do is add up all the cards that were actually used. So when we add 5 to 9, that's 14, plus 12 is 26. So we have 26 cards that were used. So if we're trying to find the experimental probability of choosing a diamond, then we're going to take this 9 and put it over that 12. Over that 26 right there. So 9 over 26, that can't be reduced, but we can divide 9 by 26, and that would give us, again, 0.346. Move the decimal 2 places to the right. So here's the second one. Again, we have 26 total. So it says not a club. Now this time, there's 2 ways we could do this. We could do the 26 minus the 7, which would give us 19, or we can just add the 3 numbers that are not clubs, the 5, the 9, and the 5. In this case, I would say it doesn't really matter which way you do it. So we could do it again, the 26, we turn this one into a 26 over 26. That would give us 19 over 26. And then divide 19 by 26, and that gives you 73.1.